So imagine if JavaScript could just read anything on your computer. If some tab in your browser just had access to reading all your passwords or knowing what your other programs are doing, that would be pretty bad, wouldn't it? By computer, I of course mean any type of computer device, including your smartphone. What would be particularly worrying is if this were to happen without exploiting any software vulnerabilities or without fooling you to do so. And that's actually the state of affairs right now. We are currently seeing a series of attacks called Spectre and Meltdown. And what I'm going to call here the Spectre Meltdown. I want to explain the core of these vulnerabilities to a wider audience. So I'm going to skim a lot of the technical details. So I'm not going to go into some of the necessary technical details to make exploitation possible. But I just wanted to give you the idea of what these vulnerabilities are doing. My name is Imer Vikosson. I'm Assistant Professor of Computer Science at Emory University. Before we get started, I just wanted to give credit where credit is due. These vulnerabilities were found by actually concurrent, separate teams that have done fine work on writing up their details, and I encourage you to look at it. So let me introduce the three ingredients that we're going to need to understand these attacks. The first one is to understand how memory works at a very high level. The second one is to understand speculative execution by your CPU. And the third one is something called side channel attacks. And actually, Spectre and Meltdown are at the convergence of these new kinds of attacks that are becoming particularly worrying, as well as hardware errors that are also worrying. So it's in this intersection of something that we're going to need to look out for the coming future. So let's get to it. How does your computer work? Well, let's take it at a really high level, very simplified view of your computer. Computer is really a bunch of different components that are strung together. These components include things for input-output, like your monitor and your keyboard and your mouse. And then there's a CPU in the middle, and that does all the processing. And finally, there's memory. And I'm counting hard disk or SSDs as being part of your memory. And really what happens when you're doing something on your computer is that you're going to load a program from a disk. It's going to be executed by the CPU. The CPU is going to do a bunch of computations. Those computations involve the memory. It's going to go back and forth, read it. And finally, it may produce some output, and that output may end up in your monitor or through a network. That's basically what execution on a modern computer looks like. So let's zoom in on the CPU and the memory. Inside your memory, you actually have the contents of all the different kinds of programs that you're currently running. This could be the programs you're running, it could be the data pertaining to them, it's data pertaining to the operating system that you're running, like your Linux or your Windows or your macOS and so forth, and it's your user data. Memory is an amalgam of all these different types of things that could be used, as well as storing intermediate computations used by the CPU. Let's look at memory a little bit more in detail. There's a lot to a memory hierarchy inside a computer. If we think about memory, it's actually very helpful to visualize it as just being a long sequence of boxes that you can open. Each box contains one bit, or 1 byte of information in our case. There are actually several layers of memory. What I've drawn here is something called DRAM, which is actually big but very slow for the CPU to retrieve. If the CPU wants to get some data from it, it has to wait for a while. So what we have are actually several other layers called cache memory. So let me draw cache memory here in front. Suppose I wanted to open one of these boxes, and I request in this fast memory over here that this particular orange box here be opened. Well, it's going to take a while. Whereas if I try to open up a different box, if I open up this one, I can actually first ask the really fast cache memory, and that has an exact copy of what I need. Now, the way cache memory is maintained is that when you retrieve something, you often take a copy and put it into the cache memory. So the next time you might need it, you have it laying around really quickly. But cache memory is small and it tends to be pretty expensive, and so you have to kick something else out. This is actually the subject of much of my research. So this is how caches work. Let's move on to the next ingredient. What are side channel attacks? Now, let me illustrate it with an example. Suppose that you are asking a computer to authenticate. and there's a particular password that the computer knows is there. This actually has happened on several routers. This is something known as a timing attack, which is a kind of a side channel attack. But I think it illustrates the point. Suppose the password is randomly Hunter2. Now, what you might do is to start guessing. You say like, well, is the password A? And the computer has to run around, check if it matches. It looks at the first character A, looks at the first character of the password, and sees that it's H. It doesn't match, so it returns. Now you might guess B. You do the same thing, and you say no. Now, of course, you could try exponentially many possibilities here, and you'll be out of luck, and that's why passwords often are good. But in this particular case, as you keep guessing, you guess G, something happens. You guess H now. What you notice is that it takes a little bit longer for the computer to respond to you. And if that happens, that was because the computer had to look at the letter H, saw that it matched, and then had to look at the subsequent letter and see if there was a match there. There was no match because you guessed a one-letter password, and the password is actually longer. So now you might actually be pretty confident, just by looking at the timing information, that the first character is H. And so you can move on to HA. You see it takes just as long as what you guessed initially. And then you might try HB, and so on and so forth, right? This actually makes password guessing linear in the length of the password rather than exponential. It's terrible. The side channel here is the timing information. It's something about the physical implementation of this algorithm, this password checking algorithm, that you are exploiting. In this case, the timing differences. So let's keep that also as an ingredient. The third thing I wanted to tell you about is called speculative execution, which might look like something like this from Rick and Morty. When your CPU is trying to execute a bunch of instructions, what it will run into is the fact that memory is slow, like we talked about. And so you have your really fast CPU, it has a lot of gigahertz, it's running around, it's executing stuff, and what it runs into is that ultimately your program is going to need some data from memory. So it talks to memory, and then you're just waiting for the response. The response takes a while. So you're spending a lot of your time just waiting for memory to respond. Now that's an absurd way of having a CPU go about its business. So 20 years ago, what people came up with was, well, what about if we just make our CPUs do speculative execution? What I mean by that is that suppose your program looks something like this. There's a branch, there's an if sentence that depends on memory in some way. And there's really only two options. Either whatever you're going to get from memory is going to be 0 in this case, or it's not. So what if you just guess? You think that maybe the most likely thing to happen in this case is that you're going to get a 0 from memory. Now, you are waiting here for memory, and you decide to just sprint ahead. You come here, and you just execute the instructions that are coming after it, even before you get your response from memory. Interesting. So if memory is 0, you're actually ahead of the curve. You know what's going to happen, and you can resume from instruction D onwards. It's very convenient. Now, if that didn't happen, if it so happens that the response from memory was that memory wasn't 0, then you actually have to roll back all the changes that you made. So you have to be very cognizant of not changing the state of the program or of the registers internally, so that you can actually go back to the other branch of that if sentence. This is very interesting. Now, the flaw that Spectre and Meltdown are exploiting is the fact that actually, when you're doing speculative execution, the state of the CPU actually looks a little bit different because of cache when it has to abort a branch. Now we actually have all the ingredients needed to explain Spectre and Meltdown at a very high level. Suppose we have our memory here. This is our slow memory. And as we talked about before, what your operating system kernel is doing is that it allocates this memory to different applications, or possibly different virtual machines if you're living in the cloud. That means that there could be adjacent parts of memory allocated to different victims. I'm pretty much describing Spectre right now, but the same concepts apply to Meltdown. So there is a part of memory here, what we call victim memory, that we want to enumerate. We want to know what it says. It could contain a password that we're after. And normally, what an operating system tries to do is to make sure that your program, including your JavaScript in a browser, cannot access somebody else's memory. There's isolation between processes. So therefore, it would be an illegal operation to try to read from the red memory, the memory on the right. What we're going to do instead is to exploit the fact that there's also the fast cache going on. Suppose we want to read this blue dot over here. There's a fast cache here in front that has copies of some things in memory. What we're going to do is the following trick. We're going to set up an array here. Let's call it A. It's a part of memory that we control. It's small. What we're going to do is that we're going to say like, well, I don't want to read the 2 elements that are in array A. I'm going to overextend. I'm going to go out of bounds. I'm going to read what's at A and element number X, where X is way too big. Oh, normally when you would be doing this on your CPU or your operating system would actually trigger a fault. It would say like, hey, this is not allowed. I'm going to kill this program. It's going to perform an illegal operation, if you like. But we're going to do it speculatively. So let's look at how that plays out. I'm going to set up something called the instrument. It's another part of memory that we're keeping out of the cache. We specifically tell the CPU not to cache any of it. It's all in slow memory. But it's consecutive parts of memory. And I'll explain what this does in just a little bit. But when I say instrument, you could imagine it being actually something like a keyboard. That's how I think about it. It's different notes. And let's see how that plays out. Suppose the code that you're executing is the following. It's a branch. It's an if sentence that just asks for something absurd. The world is flat. If the world is flat, we're going to do the following instruction. Now, normally what your CPU would be doing would be to completely ignore what's going on after this branch because it's waiting for the computations or memory accesses to figure out if the world is flat, and then it just dumps things out. But because of speculative execution, there's a chance that what's inside this branch is going to be executed. So it actually looks at it speculatively. So it's going to do speculative execution of the subsequent instruction. And in our case, when we're hacking it, we're going to run the following instruction. We're going to try to access the part of memory that lies at instrument of A of X. Whoa, that's a mouthful. Let's have a look at what that means. Suppose that what we're after is this part of victim memory, the blue dot here, and it contains the letter 4. The number 4. We don't know this, but we want to find this out. That's what the attacks are about. So what we're going to do is to look at how speculative execution deals with the following thing. The fact that it says 4, and the fact that the CPU is now executing this instruction without actually executing it, means that it's going to say like, oh, okay, I'm supposed to look at A of X. Okay, I don't know that it's out of bounds yet, because that's the role of the kernel. I will find this out later. If this was actually what's going to get triggered, the kernel will kill the program, because it's reaching memory it shouldn't. But as a speculative execution engine, I'm just going to look ahead into the memory and see what's there. And I see that it's actually the letter 4, or the number 4, or the G as a note, if you like my musical analogy. And I'm going to take that, and I'm going to look up in the instrument array at location 4, or note G. I'm going to play it. And what that does, and this is the crucial part about this attack, is that it brings that part of the instrument array into cache. That's where your timing attack comes into play. So now, the final part of this attack is that you're now going to go through and retrieve every note in your instrument. You're going to play the 0th note, and it's slow. First one, it's slow. But once you reach the 4th note, it's really fast. It's coming from fast memory. Why? Because when the speculative execution happened for the code, it rolled back all of the registers, but it did not roll back the cache access. There's leakage of information from the fact that there was speculation happening, and that speculation happened across administrative boundaries. And consequently, you're now in a situation where you can actually find out that your victim memory contained the letter number 4. Huh. And of course, we can now extend this yellow range and make it really big, maybe 256 bytes, or even bigger because caches are actually a little bit trickier. You need bigger blocks. But that's technical details. This is the crux of the Spectre Meltdown attack. So if we look at the actual code that's provided by the authors, you'll see something very similar to what I just explained for Spectre, and something a little bit more different, but still the same core idea for Meltdown. And as I promised you, I asked, well, what if JavaScript could read something from arbitrary memory? Well, as it turns out, you can simulate the exact same set of instructions in JavaScript, which means that you now have a website you go onto, and it could try to read parts of kernel memory. This is bad because it contains private information, including your passwords. And so the authors of these attacks have actually demonstrated that you could read, for instance, stored passwords from the browser. It's pretty bad. But I'll leave that to other people to explain the consequences of this attack and how you're going to react to it. And I just want to leave you with a set of URLs where you can learn more about these very interesting sets of attacks and the authors that fund them. Thank you very much.